Well, the bar magnet is producing a magnetic field down. The loop is producing a magnetic field up at the location of the bar magnet. And so this is exactly as if two magnets were oriented this way, with their north-seeking poles facing each other. And so they'll repel. In other words, the loop will repel this magnet. The force on the magnet will be up. We've just seen that for a magnet, moving as I've shown in this figure, where its north pole is facing a loop and it's moving towards the loop, because the magnetic field in the loop due to this magnet is increasing, the induced B field will oppose that increase, and the right-hand rule tells us that the current in the loop is going to go this way. And we've seen that because this loop then is behaving like, as in it's producing a field just like a permanent magnet with its north-seeking pole pointing to the left, it's going to repel this magnet. Well, Lenz's law has told us all that. What if Lenz's law wasn't true? What would happen if the reverse happened? In other words, suppose that instead of the induced field opposing the change in the B field due to the magnet, let's suppose it reinforced it. Well, so the current would go the other way, and now, because the loop is acting like a magnet with its north-seeking pole facing the other way, it would be attracting this magnet. But think about what that would do. That would mean that as this magnet is moving towards the loop, it would be speeding up. Later on, it would have gotten closer to the magnet, and it would be going even faster, which means it would be inducing a larger B field and a larger current, and it would still be speeding up. This system is gaining energy. It's gaining kinetic energy because the magnet is moving faster and faster, and there doesn't seem to be anywhere where this system is losing energy. So if Lenz's law didn't hold, this system would violate conservation of energy. And that tells us that Lenz's law is a consequence of the law of conservation of energy. Well, let's return to what actually happens. So if this magnet is moving towards the loop, it is repelled from the magnet. That means that if nobody was pushing on this magnet, the magnet would slow down. It's losing kinetic energy. Well, let's define the magnet and the loop as our system. This system is closed if nobody is pushing on the magnet, and it's losing kinetic energy, but it has to conserve its energy if it's closed. So what kind of energy is it gaining as it loses that kinetic energy? What is the kinetic energy being converted into? Well, notice that there is an induced magnetic field. And we can think back to some discussion we had of capacitors, where we realized that we can think of the energy storage in a capacitor as being because there is electric potential energy stored in some sense in the electric field inside the capacitor. Well, we can think of this in exactly the same way. We can say that there is a magnetic potential energy that is being stored in the induced field that the loop is producing. Now, I will warn you, this magnetic potential energy has to be thought of a little differently from every other potential energy we've seen before, but I won't be able to explain that for another couple of video lectures. There's nothing special about a loop of wire. In fact, a magnet moving towards any chunk of metal, such as a flat metal plate, will induce circular currents in it. We call these eddy currents, and what we've just seen is that conservation of energy dictates that they will always exert a force which opposes the motion of the magnet. Well, this turns out to be useful. In the title page of this lecture, you might have wondered what this picture was showing. Well, it's showing a piece of a roller coaster, and what it's focusing on is these things here, which is an eddy current braking system. They're just great big magnets. And the train of the roller coaster has big flat metal plates, and when the train comes past here, the plates pass between the magnets. Eddy currents are induced, and these are the brakes for the roller coaster. Here's a demonstration of eddy current braking. Here's a great big magnet, very strong. And note that here is an aluminum plate, and the aluminum plate isn't attracted to it. However, if I drop the aluminum plate between the poles of the magnet, you'll note that it falls rather slowly. It seems to be slowed down. There's a force resisting its fall, unlike this piece of plastic, which just falls straight through. The aluminum plate has eddy currents induced in it, and those exert a braking force which makes it fall between the poles very slowly.